Hi everybody, I'm Sidharth Gupta, and today I'm going to talk about a new method for fast optical system identification which can be applied to scenarios where we're imaging through scattering media. So what is imaging through scattering media? So let's say we have some fog and there's an object that's in this fog or behind this fog. The light coming from this object will be scattered in all different directions, and our task would be to capture this light and try and reconstruct an image of the object that's in this fog. Furthermore, if we can actually mathematically identify this optical system and come up with a mathematical model for it, we can actually apply this in optical computing. For example, we can replace random dense layers of neural networks with actual physical optical scattering medium. And since we've identified what this system is and we have a mathematical model for it, we can backpropagate through this optical media and actually backpropagate it through this entire neural network and train it. And the idea is that these optical neural networks can be much faster at performing machine learning computations than their CPU and GPU counterparts. Now, there are various algorithms and techniques to image through scattering media and try and identify random scattering media. However, due to some physical limitations, which I'll get into momentarily, these algorithms are very time-consuming and computationally expensive, which limits the scale of the imaging that we can do. So to understand this better, let's look at the imaging process. So we have an illumination source that illuminates some image, and we get a light field at the input X. This then interacts with our scattering medium, and we get an output light field in the detection plane, which I'm going to call Y, and Y is linearly related to the input X via a complex matrix A. And so therefore, each element of Y is also complex valued. And in many typical scenarios, A is an IEEE standard complex Gaussian matrix or approximately IEEE standard complex Gaussian. And this looks great because I have Y, and if I know A, I can perform simple linear inversion and get X and figure out what the input was. However, we actually have to capture all this light information, and we do this using a camera. Now, cameras can only measure intensity, and I'd mentioned that Y is complex valued. However, we only get the element Y's magnitude of each element of Y. And that's still probably okay because there are algorithms to solve such problems such as absolute value of Y squared equals absolute value of AX squared. However, a lot of these algorithms typically require us to know what our transmission matrix A is. And so we would have to calibrate this. So therefore, our goal today is to come up with a method to rapidly learn what this transmission matrix A is. And this is becoming increasingly important because in many typical scenarios, the dimension of Y is much larger than the dimension of X. And so if we have very large images, our transmission matrix is large, and it becomes quite computationally demanding to try and learn and calibrate the transmission matrix A. So how can we go about doing this? So let's say we have k known calibration signals, which I'm going to put in this matrix Xi. I'm going to put these into my optical system and measure capital Y absolute value squared. After this, my goal is to then try and learn A from capital Y absolute value squared. And there's an existing method to do this, and this is called double phase retrieval. Here, basically, if A has m rows, we solve a quadratic equation and recover each row of A separately. And there are GPU implementations of this double phase retrieval method, and for a matrix of size 256 squared by 64 squared, it takes about 3.3 hours on a GPU. And then we would then also have our measurements, small y absolute value squared, which are due to the actual signal that we care about in the first place. So we can use our learned transmission matrix A and some existing method to recover X from its absolute value measurements. In this talk, we're actually going to propose a new method to learn a transmission matrix, and that's going to be called measurement phase retrieval. So here we're going to try and directly recover each element of capital Y and solve a linear system like this because we already know what Xi is, and if we recover capital Y, it's just a simple linear system, and we can use a lot of different established methods in order to recover A and solve this equation. And amazingly, we can actually recover capital Y without knowing A. And we've done this before in a prior work, and we're going to show an even faster way to do that in the remainder of this talk. And on a CPU, if we use measurement phase retrieval, we can calibrate a matrix of the same size in 6.2 minutes, while the GPU took 3.3 hours. So let's really hammer this in and understand this clearly. Instead of solving absolute value of y squared equals absolute value of a psi squared, I'm going to recover y, and because I know what psi is, I'm going to solve this system for a. And I can control and design psi however I want. So I'm going to make sure it's full row rank. I'm going to make sure there are plenty more columns than rows, and then I can use the simple least squares fit and the pseudo inverse to recover the transmission matrix A. Furthermore, I can actually do this efficiently if I design psi by concatenating two different circular matrices with each other, and then compute the quantity y psi pseudo inverse using the FFT. And later on in experiments, we'll see that this can be much more efficient. So before we get into measurement phase retrieval and how we do it, let's look at some experimental results and convince ourselves of the promise of this method, which I'm going to talk about today. So we use in our experiments an actual hardware system, an optical hardware system, and over there we imprint our signals onto a coherent light beam, which is then shined through a multiple scattering medium, which acts approximately like a standard IED complex Gaussian matrix, and we use an 8-bit precision camera to capture the scattered light. So there's noise in our actual camera measurements because it's only 8-bit precision, and this is a hardware system, so there's inevitably some noise elsewhere as well. And as a reminder, double phase retrieval for a matrix of this size took 3.26 hours, as I mentioned before. And these are the timings for matrices of various sizes using measurement phase retrieval and then solving the linear system y equals a psi. And so we can see in blue that it takes 6.15 minutes for a matrix of the same size. And in fact, we do matrices of much larger size in a fraction of the time. And we can now go forward and look into how we actually do measurement phase retrieval in order to get such timings. So let's first consider trying to find a phase of a single measurement. So let's put in one calibration signal, psi1, and interact with one row of the transmission matrix A, and we get absolute value of y1 squared. And we're going to call this a squared distance to the origin, and this is going to be y10 squared. Let's call the origin R0, and let's say we also know two other complex numbers on the complex plane. And we know that y1 is complex valued, and it lies somewhere on the circle of radius y10. However, with this information, we can't actually find out where y1 is on the complex plane. But let's say we knew a few other distances, namely the distances between y1 and r1 and r2. We can see that they all meet at one specific point, and via trilateration, we're able to localize y1 and get its measurement phase. We can repeat this process using the same R0, R1, and R2 for the next calibration signal, and the next calibration signal, and all our calibration signals, and we can identify all of them on the complex plane and get the measurement phases. So central to this method is trying to measure distances in order to perform measurement phase retrieval. And so the question is, can we measure distances on our optical systems? And the answer is yes, and we're going to go through how we do that now, and we're going to call this numerical interferometry. So we have k known calibration signals, and we have at least 3 known anchor signals, and this is because, as we saw previously, we need at least 3 points in order to do trilateration. Now, we're going to outline a process that can get repeated for each row of capital A. So let's just pick small a, which is one row of capital A. So we're going to assume that the interaction between anchor signals and small a is known. Now, our unknowns are the interaction of calibration signals with small a. Now, we need to measure distances, and how can we do this? So let's interfere calibration signal k with anchor signal s, and we're going to get this blue quantity as our measurement. Furthermore, if we actually expand this inner product, we'll see that's exactly what we want. It's a distance between a complex valued number which we don't know, and a known complex valued number. And this is exactly what we had on the previous page when we did trilateration. And we're going to call this numerical interferometry. And because we're numerically interfering these signals, and generally in optical interferometry, you would have to do this optically by interfering a signal with another coherent beam and modifying the phase of that coherent beam. And those systems can be quite sensitive to noise and other environmental factors which our numerical method doesn't have to encounter. So let's expand out this distance a little bit more. And we're going to interpret complex numbers as vectors in R2 over here. And we can rearrange and write it like this. And I mentioned that we need at least 3, or we have S anchor signals. So let's stack those on top of each other like this. Now, we have actually K calibration signals, but this is only for small k. So let's horizontally stack all of those next to each other. And we end up with this simple linear system. And we want to recover the matrix W when we have E equals MW, and we want to recover the elements of this matrix W. And we can just use simple pseudo-inverse to do this because M has 3 columns and it's S rows tall, and S is typically in our experiments about 10 or 20, so it's extremely fast to compute this pseudo-inverse, and we can very rapidly get W. And we can then take the top 2 rows of W, which are the real and imaginary parts, of all the calibration signals interacting with row A of our transmission matrix, and basically this gives us a row vector of length k. We can just repeat this process for every single row of capital A, and we would obtain capital Y in Y equals A CASSP. And we've done it. We've done measurement phase retrieval, and we haven't even had to know anything about capital A. However, there's one thing here. I mentioned that we know how the anchor signals interact with each row of our transmission matrix, and those were these green values. However, in reality, we don't, and we would have to figure this out as well. So how can we do that? Well, our solution is, again, interferometry and numerical interferometry. Let's numerically interfere all pairs of anchor signals with each other and put them into our optical system. And again, we'll measure distances between 2 points for all pairs of anchor signals. And so then on the complex plane, we have a bunch of distances, and our task just boils down to identifying a realization of points on the complex plane that satisfies all of these distances. And so we do this by multidimensional scaling in our paper. And once we do this, we have a realization, and then now we have our known points in the complex plane, and we can then go through the rapid numerical interferometry process, which I described earlier. So let's actually verify some aspects of our method experimentally. So we use the same hardware setup as I described before. And now we actually take the learned transmission matrices, which we recovered, actually use them to do imaging. And so we try and reconstruct X from AX absolute value squared using the learned A. And so the top row are the original images, and the bottom row are reconstructions for images of various dimensions and various oversampling ratios. And so we can see that we're actually recovering physically plausible and viable transmission matrices, and we're able to do real imaging and use existing algorithms to do imaging using our learned transmission matrices. Furthermore, I mentioned that we can actually use the FFT to solve our linear system Y equals A CASSP when we've done measurement phase retrieval. And we can see that indeed, as the signal dimension increases, the FFT starts to show increasing gains, and it should be the method of choice when using measurement phase retrieval and numerical interferometry. So in summary, we can do measurement phase retrieval via numerical interferometry, and we change learning and transmission matrix into a linear problem instead of a traditionally quadratic problem. And this method allows us to learn transmission matrices that can be used for imaging even when we have noise in our optical measurements. Please do check out our paper for more details and for a link to code.